is an algorithm where I don't have A hat and B hat. I don't try to estimate them, because here when I say A hat, B hat means you have behind this algorithms that will use this square method, that will create the data, that has maybe latency, anything
To
of
give
this
out
sort.
the A and B.
Sorry?
To give out the
to give it A. So there is background there. It's not only A hat and B hat. There are functions that you are doing entirely in order to get it. So the first method that you are going to see is called the MIT rule, and this is maybe the first rule that have been implemented for adaptive control. Right? So what I'm expecting you to learn from this lecture, first of all, I would like you to grasp the basic idea of model reference adaptive controllers, in particular the fact that now we are talking about a performance index, something that we are going to take to see how well we are doing. And then I would like to identify properties of this model reference adaptive control. We would like to grasp the MIT rule. In particular, what we would like to grasp in the MIT rule is not only how to apply it, but what are the weaknesses and pros of the MIT rule. What do we have in the MIT rule that is not sufficient? And what is good for us when we use the MIT rule? Up to here, up to this MIT rule that we are going to do up to this level, we are going to talk about input-output adaptive control, so an output feedback. To explain how the MIT works and what are the weaknesses of MIT rule, we have to run to Lyapunov theory. And based on the Lyapunov theory, we have developed a new theory. So we use Lyapunov to explain how the problems with MIT rule. And then from this development, we developed a new method using the Lyapunov directly to develop adaptive control. So if you would like to go to multivariable, this would be one of the cases that we are going to use. If you don't have decouplers or you don't have anything that separates your system to single input output, then you need to go to, otherwise it will be complicated. Now, the problem with adaptive control is that it's basically a state feedback. It's no longer an output feedback. Right? We are no longer looking to the output of the system and trying to do the control based on that. So we want to show in these 2 points how Lyapunov can be equivalent to the MIT rule in certain cases. Everybody is okay with that? So if you would like to know the structure of how we are going to present, first of all, the MIT rule, then we are going to criticize the MIT rule. We go to Lyapunov and we see the advantage of Lyapunov. Then we use Lyapunov to design the controller. Then we are going to ask ourselves, what's the link between Lyapunov and the MIT rule and when they are equivalent? Okay, because the two controllers are different when we are looking at them, but there are cases where they are equivalent. Everybody is okay with this?
Yes.
Right. When we go to see the equivalency, we need to look to passivity theorem, small gain theorem, and many other properties that are normally part of nonlinear systems. But we have no choice. We will go through them very quickly, not in depth, but at least it gives you the idea of how they are working together. So this is our objective for this couple of weeks. So the material that we are going to cover, we are going to start with the MIT rule. After that, we are going to see how we are going to adapt the gain of the MIT rule, do some simulation here and see how it works. We would like to analyze the stability of the MIT rule. And once we study the stability of the MIT rule, we go to Lyapunov. Then we design through Lyapunov. Then we look to stability in Lyapunov, LiPo stability. Then how to apply it to adaptive control and the relationship between the two. Right? Everybody is okay with this? So now the design is a shift from what we did before. Before we assumed that the controller is formed of 3 polynomial RST controllers. Now we are going to impose a structure on the controller, and usually we use only gains. We don't use polynomials. Everybody's okay?
Yes.
So this is our structure then. Our structure basically is this. We have a reference model, and this reference model, our reference signal. This reference signal goes through our reference model that we have here. We have the plant, it gives me the output. I compare between the reference and the plant, and based on that, I can get some adjustment mechanism, and this adjustment mechanism comes here to the controller. Right? And this is how I'm going to do it. We'll see some application of this through examples. So we continue with this. This is the MIT rule. So basically the MIT rule says very basic questions. It says if I would like to look to E of t, which is the difference between y and y of m, and I would like this error to be 0, I'm going to declare an index function, a value function, that I will call g of theta, because it depends on the parameter of the controller, that is equal to half of the error squared, and my objective will be to make this minimum, close to 0, minimum. Right? This is as simple as that. This is how the MIT rule works. Now, if I look to this function here, I'm going to show you one example of how this function looks like. Everybody see how the function looks like? So this is how the Lyapunov function or this index function looks like, or the way I would like it to look like. What my target, this is all the parameters, multi-parameters that are here, and my objective is to be at the minimum, completely at the bottom. Everybody is okay with this? So if you look to this function and you see how it's moving, we can look to what we call the gradient function, or the gradient plot. And the gradient plot is telling me that all the gradients are pointing upwards. So this is the minimum, and then everything goes up. It increases with the change of theta. Right? So if my parameter changes, for example, in this direction, the gradient, which is the derivative of my function with respect to the parameter change, will be pointing upwards. Right? So anything change, any positive change will introduce a positive change, an increase of change. Everybody is okay with this? Yes.
How is it going up? I'm not getting why is going up.
Y is going up. If you look to this function here, see this is the minimum, and if you change this parameter in this direction, the function is going up. Otherwise, this point is no longer a minimum, right?
Sure.
So any variation of this parameter in this direction will introduce an increase. Any change of this parameter in this direction will introduce an increase of the first. So the derivative are going up. So the MIT rule says we can develop a rule that goes against the gradient. So basically, I look to the gradient of the function, and rather than changing my parameter in this direction will give me an increase. So I will change it in the opposite direction. So I can go in the opposite of the gradient. Everybody is okay with this? So if I go to this side, for example, to the negative side, if I move in this direction, it will be increasing. So the negative direction will be to go back to 0, the opposite of the gradient. The idea is clear, right?
Yes.
All right. So now if you go back to the MIT rule, so if I look to the change of the cost function with respect to time, the cost function is function of the error and time. So the error is dependent on time, and the error, the parameter inside depend on time. So the derivative of this function with respect to time is normally the derivative of j with respect to the error times the derivative of the error with respect to time plus the derivative of j with respect to theta multiplied by the derivative of theta with respect to time. Two parameters, right? Because theta also depends on time. Theta is your parameter that you are trying to change, right? So if I look to the derivative of j with respect to e, this is e squared. So derivative with respect to e is basically 2e times half. It will give you e, right? So will be e multiplied by the derivative of e with respect to time plus derivative of j with respect to theta is equal to the derivative of j with respect to e multiplied by the derivative of e with respect to theta multiplied by the derivative of theta with respect to time. You agree with this? You agree with this?
Yeah.
Derivative of j with respect to e, we said it's e squared. Derivative with respect to e is 2e times half. This is e. So this one is e. Then we have e derivative of e with respect to theta multiplied by derivative of theta with respect to So an ideal choice of derivative of theta with respect to time. So I'm imposing the derivative, how the theta will change with respect to time. Alright? An ideal selection of the derivative of theta with respect to time that will go and will give me derivative of j in the opposite direction of the gradient is if I put derivative of theta with respect to time equal to minus e derivative of e with respect to theta. Right? But in order to give weight to this, I can put a factor. So this factor is a factor that I will select. I can put equal to 10, I can put equal to 1, I can put equal to 0.1, but it's a factor, it's a weight that I'm going to give. And hopefully the weight that I'm going to give, it will basically based on this, it will give me, the 2 will give me this function here. Derivative of j with respect to theta is equal to e, derivative of e with respect to time, minus gamma, derivative of e with respect to theta squared times e squared, right? Because you have here derivative of theta with respect to time will give you e, so e times e is e squared. Derivative with respect to e with respect to theta times derivative of e with respect to theta will be derivative squared. And we sign minus gamma, right? So we will have here minus gamma, the derivative of e with respect to theta, the whole thing squared, times e squared. And the selection of gamma is going to make this term more relevant than this term to force this derivative to be negative. So if j is a positive function and it's 0 only when e is 0, and the derivative of this function is negative, then it will go to 0. Right? Repeat this again.
Yeah.
So if this function is positive, right? I showed you the function is positive.
Yeah.
And the derivative, if I select the derivative of this function negative, right? And it's 0 only at 0, then it has no choice only by going to 0, because it cannot be negative. So like this, I will make sure that the cost function will be decreased to minimum. The problem is that term is not clearly negative, right? This term, based on this term here, based on the selection of parameter, could be positive. So we need to have a proper selection of gamma in order to make sure that this will be negative, will go stable. And this is something that we would like to understand how. So the first question, the selection of this derivative, we are okay with this? We are fine, we understand it? We would like to understand, so this is question for us, how to select gamma. Because here somebody can say gamma could be as big as possible. If gamma is as big as possible, gamma is positive term. Theoretically, if gamma is very big, then this term would be more dominant and it would be negative. Right? This is the intuitive type of thing. But we would like to see what will happen if gamma is big, and is there a limit for gamma, and how can we find this gamma? So this is the question that we'd like to answer.
But if we take big value of gamma, then that term will be in the negative term. Right?
That's right.
So it will be reduced.
This term is always negative because it's a square. Square is square.
Square is square, yes.
Right? But this gamma big, in this cost function, it gives you the impression that it's going to be negative under the assumption that this is small.
Yes. No, this is small. But the value of that side will be less if we.
That's true. But this
big
side,
gamma.
E would be big, but the change of E with respect to theta could be small. We don't know. So, but when you say this is very big, it's like looking to the whole thing and saying this is dominant with respect to this. But if the error goes to infinity, the change of the error with time will go to infinity. So this is double infinity. And here the change of the parameter with respect to theta could be very small. So there's no clear conclusion that we are able to make from here that says that selecting gamma very big will guarantee for us that we will go to zero.
So gamma here it's not constant.
Gamma is my selection, it's a constant.
It's constant.
Yes, but there are people who use PSO to select gamma. Some of them they use the fuzzy logic to find gamma. But in our design, we are going to assume that gamma is constant. We can make it time variable. We can use advanced algorithms. Adaptive of gamma. What I'm saying makes sense? أنا عارف إنه رمضان بس I'm seeing your faces. Makes sense?
Yes.
All right. I think the best way to do this so to understand how gamma works is by looking to an example. But these are other variant of the index function. I showed you the square function because it's smooth. We are able to make the derivative. But there are other ways to make the cost function using absolute value of E of t. At that time, we are going to select derivative of theta with respect to time is equal to minus gamma derivative of E with respect to time. Time is sine of E. Rather than E, we are going to put sine of E. And sine of E is the most important one. Basically, if I come here and replace E by sine of E, nothing will change. Because the value of E will go to the value of gamma. It's like we are making variable gamma. What is important in this is the sign of E. E increasing or decreasing. If I select the value function, this is not derivative of j, this is j of t, then we are going to have this derivative of theta with respect to time, which is minus gamma sine of the derivative, time is sine of the, and again, if I look to this, and I say, what is important in this formula? What is the sign? Because gamma is a rate at which I'm going to do, so everything will go as if I change gamma. So what's important is the sign. So all of them are equivalent, but they exist. We call this the sine algorithm, this one is the sine-sine algorithm. Okay? The problem with the sine-sine and the sine algorithm is the jump that you have in the sine, but you are able to make the sine smooth by approximating it with the error function. So this is not an issue. So that's it. This is the rule. Derivative of E with respect to theta. This is the rule that we are going to adopt. Derivative of theta with respect to time is equal to minus gamma E derivative of E with respect to theta. Theta is not one parameter, it could be a vector. So we are going to have as many derivatives as the parameter in that vector. Right? But this is the rule. So derivative of E with respect to theta, we call this the sensitivity derivative. So how sensitive is the error to change of parameters? Right? So this is the concept of this. We are saying that the parameter changes are slower than the other variable in the system. You remember we talked about this before several times. And we said that we are going to assume that the dynamic of the system is faster than the change of the parameters. So if you buy a car, you are using the car faster than the change, which is every 5 years, for example, or every month. And the derivative of E with respect to time, we are with respect to theta. Since it's a partial derivative, we make the derivative as if theta is constant. Why? In terms of time scale, theta changes, but theta is slower than the system. So the system, if I am in the system, I will say theta constant when I move. So this is the first example, and I think this is the best way to do it is to go through examples. Yes, please.
When you say the parameter changes are slower, it means that the controller will be able to get the values, then the system, the parameters will change after the controller get closer. I mean,
Not only the controller, after the system, you mean? That's what I'm saying. The system gets closer than the parameter changes. This is what you're saying, right?
yes, I mean the system change in the parameters of the controller will be able to give the controller the parameters that will make it close to the model that we want.
Yeah.
Then the system will change again, and so
Exactly. So this is how you are going to see it. Huh? So if you look at this loop is faster than anything else here. So the system, when you have a change of parameters, will have the time to reduce or to arrive to target before your parameter changes again. Otherwise, you are going to be always
Late.
trying to catch the ball.
exactly not be able to catch.
If theta is constant, why do you need a delta?
Who's constant?
Theta.
Theta is not constant. Theta is changing, but if I am in the system, I will see it constant because it changes slower than the system itself. So this is a good question. So we are assuming theta is changing, but the way theta changes, the parameter changes, is slower than this loop. Okay. So basically, if I have 10,000 feet and I would like to reach to this 10,000 feet, and my controller is changing, and I did not reach the 10,000 feet yet, I will have a problem reaching to this point, because every time we are going to have a change of parameters, and the controller is not able to reach this 10,000.
Yeah.
So what we do, we divide this 10,000 feet in different levels, 5, 7, 2, 1, and we say 1, and then it reaches 1, then it changes of altitude and changes of altitude. So when you see the control design of the airplane, for example, we have a range. We say from 0 to 1, we use only this controller. From 1 to 5, we use this controller.
Okay.
But the controller is changing. Overall, it's changing in terms of time. Okay? But if you are in the system, you will see it. The system sees constant for a period of time until it stabilizes, and then it changes again. So rule of thumb, as we said last time, it could be that the parameter changes 5 to 10 times slower than the system. Right? If they are fighting, if they reach, and there is no time separation between the two, the concept is called time separation. If there is no time separation between the two, then you will be always fighting, trying to catch up with the controller, and you will never be able to separate.
So if we have a control system running on some microcontroller or microprocessor, so basically we will have to run two loops, one for the current controls and the other for the system identification. Have to
Why not doing identification right now? No identification.
Yeah, so it will just find the parameters for the controller, and if the new updates is available, then it will change the controller.
So
Otherwise, the one loop it will
the other one is continuing.
continue.
Continuing all the time. It does not mean in the implementation you have two time constant, two simple times. Right? You can work with one simple time. Every 0.1 second you make everything done again. But physically what is happening on the system is that data during this particular period, or the model of the system, the parameters that are changing during an interval of time appears constant to the system. So the system is able to achieve something.
But if you have a first loop, and in each loop we get the the new updates of the controller. So it means that we can use the new updates of the controller, the parameters of the new controller. We have to stick to the.
But you can imagine yourself like this, and you are playing a game. I don't know if you want to play it, but
It's a stable point. If you keep changing the parameters of the controller.
that's right. Suppose that you stand up right now, and I will order you to go to left and right. So I will tell you go left and then go right. Right? So you go left, and I give you the time to go to the right point, and then I give you the time to go to the left point. You want to test it? Anybody wants to play? Alright? We need somebody active. So if I tell you to go to the right, and then I wait until you reach the right, then I tell you go to the left, and you wait until to go to the left, then I tell you go to the right, and they keep like this. If I increase the frequency to go to the left and right, what will happen?
We'll start somewhere.
You'll never reach left, you never reach right. So this is what I'm saying. We are saying that there is change of parameter, change of controller, but we are giving the time to the controller to reach a point, to the system to reach a point.
The example is, I think it's about the gain margin.
Not gain margin. Gain margin has nothing to do with that. Gain margin,
Like the one stuck somewhere, it cannot reach to the extreme position, the commanded position.
but it's not gain margin. It's not. I'm pretty sure he has a very good gain margin. You want to test it? To go left and right? But what I'm saying is that this is time separation. Time separation between two orders. Because when I give him the order to go right, he got this as a request. So he has his own controller that will push him to the right. But his controller, it depends on the actuator, the muscles, the speed, age, blah, blah, blah. So when he tried to do the action, I changed the command for him. So if my change of command is faster than he can respond, he will never able to be, he will never move. He will stay exactly on the same point. Everybody understood the time separation in principle? So I need to give the system a chance to be able to do something. And for that, I'm telling him, look, I'm changing for you the instructions. The instructions are time variable, right? To go back to Hamlet remark. But every time it changes, I give you the time to reach something, to reach a point. Such that at the end, you are able to reduce the error. Otherwise, you are going to stop and tell me, every time I try to do something and you change the direction of the instruction, I will not be able to do anything, and blah, blah, blah. And you may have felt this, right?
But sir, if system does not reach at our desired time, then
System does not reach at the desired time.
yes, sir.
This is
If
the,
if
this
you
is
want,
the,
if you want the system to reach at that point in 5 seconds or 10 seconds, but it reaches at 15 seconds or 20
Right.
seconds.
if we have a time request, it will not be like this. It becomes like a optimal control where we have a time target. But here our specifications are here. So when I say the system arrives to something, it means that he was able to reduce the error between the reference y and y, which is what I want. Does it make sense?
Yes.
So basically, you need an expert for this control.
You need an expert?
Yes.
You are expert.
It's just a mechanism. For example, airplane. How do you know? For example, from 0 to 1, do this. From 1 to 5, change this.
You need to know that your airplane is able to give you the performance model that you want. This model. If your system is not able to give you this performance model, then you will not be able to reach it. Whatever you do. You understand what I'm saying? So do you need to be expert in system? As a control engineer, you need to be understanding the system and work with an expert. Right? Work with somebody else. For example, when we developed control system for turboprop engines. Turboprop engines are engines with propellers, big propellers. You see that some of the airplanes that take off in Marawa. And we understand exactly how the airplane works. But we have Alstom from France who came to Canada and said we would like to develop high-speed train. And we would like to use the same turboprop engine, but we don't propeller, of course, but only the gas turbine engine. But we needed to understand how the train works. And we are not claiming that we can understand everything, but we need to sit with somebody who understands it. If I do this, what will happen? What are the functionality? I talk with him, he understands. what is going on. He explains what is going on in the system, and then you learn from him, and he learns from you. So normally, some of the, by the way, this is maybe a code because many of our students, when they graduate from here, they think they are gods when they go to the industry. Some operators know better the system than any engineers. The operators, they are just technicians. So the best person to sit with to understand how system works
Okay.
is this operator. He may know better than any other engineer. Alright? This is just a code. Yeah. Thank you. Alright? And it happened to me. I was sitting with operator with gas turbine engines, and they told me if I do this controls command, the engine will surge. And I was at the time new hire, so I said, no, I'm PhD, you cannot. I know exactly what I'm going to do. And when he does it, it surges. So I started changing my attitude. So I sit with him and say, this is what we are going to do it slowly, do it this, what do you think will happen? Blah, blah, blah. And he explains, sometimes we change, sometimes he goes with what I suggested. This is how things work. Okay. Make sense for you? All right. So the first example that we are going to take is this. This is a very simple example. We call it the feed-forward gain. And basically what we have is this. We have a transfer function, y equal to k times g of s. So what I assume in this transfer function is that the dynamic part I know, but the amplification I don't know. What is unknown in the system or changing in the system is k. But this part, g of s, is known and it's not changing. It's not dynamic. This is our first example. So it's just a feed-forward gain that we are trying to not identify but adapt to each changes. And then the desired response is requesting from me that this system has to work with this amplification, K0, required K0. So example, suppose that the required here is 10, but this gain is sometimes 0.1, sometimes is 1, sometimes is 5, sometimes is 10. So since this is changing, I don't want to know the changes. What I want to know is this system behaves like this system with a gain fixed equal to 10. Everybody is okay with this? So the first step I do is to design the controller. And this is what I was saying about imposing the structure of the controller. We did it before as a polynomial. Here it's only just control gain. So we are assuming that the control signal is equal to theta multiplied by the reference. And what I'm going to do is to find what should be theta and adapt theta to the change of k. Is it simple? Very simple, right? So when I look to the difference between the two, the system and the system, the difference would be the control. I replace, there is u missing here, huh? I will add
Yes.
theta. Yeah. So if we put u equal to theta times uc, we will have theta times k minus k0 multiplied by g of s, the whole thing multiplied by u of c. And this is my error. Everybody is okay with this? Simple?
So we want theta k minus k0 equal to 0.
We
But
want to make it minimum
This
and ideally equal to 0.
is what we'll take out.
Yes. So now I just say y minimum because maybe there is a disturbance that is in the value of y, but I'm not seeing it, so I'm
So it's
trying
not
to make
there,
sure.
we'll not take it.
Yeah, so we'll make it as small as possible. Alright, so my tracking error is basically E equal to y minus yn, which is equal to k times, and here, you see here I replaced s by p, by the operator. Why?
Discrete.
Because
Discrete.
p is continuous, not q. P. Why I replaced s by p? Why did not continue with s?
We are working on discrete. We
Might
are
want to
working on
convert
discrete.
it.
We are continuous.
Well,
G of
might
s
want
is the Laplace transform.
First loop, have S and T.
We have s and t. I have t from this side, which is u times the reference and theta, and the half from the left hand side is the Laplace transform. I cannot mix Laplace and in time domain. But I can say this is the operator. So if somebody will ask me, what is the Laplace transform of this? It could be very complicated. It's not only GP times theta of S times UC of S, right? It's a convolution. It's more complicated than this. So this is why I'm using P, because it's mixed between time and Laplace. And this is very important point, because when we are going to do the analysis of stability, I would like you to remember this point, that we are mixing time and Laplace transform. And the Laplace transform of this term, it's not G of S times theta of S times U of C of S. It's not. It's a convolution of this equivalent time domain GP with theta of T times U C of T. Convolution of T.
Can we have the inverse Laplace of the G of S and put it here?
Sorry?
The Laplace inverse.
Yeah, we can put Laplace inverse, but if I put Laplace inverse here, it will have to be the integral and the convolution between the three signals. You understand what I'm saying here, huh? Because this is not a multiplication in time domain, and it's not a multiplication in Laplace domain. It's an operator in Laplace operated to time domain. So it's a convolution. Convolution means the integral from minus infinity to infinity of t minus t tau times g of tau. And then you have to go back and make the convolution of these three functions.
So if we implement the same thing in a controller like microprocessor, we have to make this.
We did not derive to the microprocessor. Just wait for the microprocessor. Because this I will not put in the microprocessor. What the microprocessor needs to know is theta. And you do whatever you want with the calculations. Alright? So the rule says to change theta, to find how you are going to change theta. You are going to make sure that derivative of theta with respect to time is equal to minus gamma times the error times derivative of the error with respect to theta. We're going to modify exactly this. So this is gamma. I called it here gamma prime. You can call it gamma 1. This is not derivative. This is just another gamma. Right? And now you know why later. Right? Multiplied by E multiplied by the derivative of E with respect to theta. So this is what it is. Derivative of theta with respect to time is equal. I'm going to use here gamma and then I will change it later just to make it easy for you. It's equal to minus gamma times E, derivative of E with respect to theta. And this is equal to minus gamma times E, and the error is this. Right? This is the error. And the derivative of the error with respect to theta, this term is 0. All what remains is
The left.
this term. So the derivative with respect to theta would be K GP applied to U of C. Why I was able to do this? And then we come back to Hammer's clause. Why I was able to do this? Why I was able to get theta out? We said theta, say it does not make any sense to say derivative of theta with respect to time is equal, so this means that theta is variable, a function of time. And then come back here and say I took theta out because it's the derivative.
It's constant.
Because?
Constant.
Because we assume that theta is almost constant for the system. The system sees theta constant. This is why I was able to take it out of this derivative.
It's linear or
If you want, it's like bi-interval. But the system, if I'm sitting on the system will look to theta and you'll see during the radiation theta is constant, so it takes it out. But theta is variable with respect to time. If I see that theta does not appear constant, which means theta is varying at the same cycle as the system, I will not be able to separate theta from this derivative. Because GP is applied to theta and UC. It's a convolution between three signals. To take this theta out, it has to be constant. So it has to move or appear slower during the cycle of control. Everybody understood what I'm saying here? Everybody understood why we assume theta for the system appears almost constant? Yes.
Does that mean that what we impose on the system, that the input is equal to theta, then multiplied by the reference, is a must, because
What
if
do
we
you mean is a must?
impose something else, the relationship between the input and the reference, U and UC,
Yes,
then this expression is going to give us something in terms of theta.
that's right. But during the time of control, theta appears constant. It's the same. Like I'm go to the right. This is the command. This is the theta, or you go to the right. And during your time or time to reach right, this remains constant. But I can change it later until you go to the left. You understand what I'm saying? Everybody understood the importance of this assumption? طبعا this assumption it has an implication in your design. For your system to work, you need also to make sure that this theta is really slowly changing. The parameter of the controller is slowly changing. Alright, so here we have an issue. The issue that we have is that we have in this change of theta, this is the change of theta, the change of the parameter that I need to put on the controller varies with respect to time, but it's function of k, which I don't know, right? And it's also function of GP convoluted with UC. This is something that it's kind of a response to the system, right? And it depends on the controller itself. So by itself, if I look to the system, it's not, I cannot implement it. I have no idea what k is. So how can I implement this derivative with respect to theta, with respect to time? Everybody understood the problem that we have here? So if I repeat what we did, we first of all put the output y. So this is our system. So this is our system here. Then we put our reference model. Then we selected the structure of the controller. The structure of the controller is theta multiplied by UC. It could be any other structure. You will see different structures. Then after that, I computed the error. Then I implemented the rule. And when I implemented the rule, I found out that the rule depends on parameters that I don't know. K and GP convoluted with UC, or GP applied to UC. So since K0 is a constant that I know, I'm going to multiply by K0 from this side and divide it by K0. K0 is coming from my model, my reference model. Now when you look to a reference model, we go back to our previous equation here. Ym is equal to K0 G of S applied to UC. So I'm going to say here this is Ym. And Ym is the output of my reference model. So I just take this signal and put it there. Right? Everybody understood that?
Yes.
So I have no longer a convolution in my microprocessor. It's just reading the signal and bring it back directly to the system. Everybody understood what I said here?
Yes.
Now this gamma is a constant that I'm selecting to control. And these k over k0, I can put them inside gamma. So gamma is, for example, I want gamma equal to 10, right? Or the value of gamma is equal to 10. And this one is equal to 5. Then it's like I'm using gamma equal to 50. And then remove the signal. This issue. So I'm going to come back here and say this is equal to minus gamma 1, another gamma, whatever it is, it's your selection, multiplied by Ym, multiplied by E.
But sir, I thought k was the unknown.
K is unknown, but it's K over K0 is a ratio. It could be 1, 10, 4,
I
5.
choose it.
We don't choose it.
You don't choose it.
We don't care about it.
I
So
don't-
si-
I don't
suppose
know
that,
K.
huh?
I don't know k. How can I know that?
Suppose that, for example, that you selected this one equal to 50. Because this is what you are going to implement. And it happens during this period that this one is equal to 10, the ratio. You don't know what is the ratio, but it happens that it's equal to 10. This is equivalent to using this one equal to 5. So you don't care. Just put 50. And if, for example, if this one is 10 but you selected 5, it's like this one is 0.5. So it will, this gamma will absorb this.
Complete.
It will compensate. Exactly. Is it clear what I said here? So in the slides, rather than ending with gamma 1, we started with gamma 1. So we came here and we said this is gamma prime, or gamma 1, this is gamma 1, and then we are going to call this gamma. Everybody understood? So in the slide, since we knew that we are going to arrive with another gamma, so we just renamed it from the beginning, so we can get a cleaner.
Sorry. So based on the explanation you made just now about the relationship between gamma,
Yeah.
gamma 1, k, and k naught.
Yes.
K over k naught is a ratio, but it's unknown,
Yes.
and it's something that depends on the system. Since k is from the system, we
That's right.
actually have.
But during the control, this k is constant.
Yes.
Okay.
But then in the case scenario, because again, we don't know how this system is going to behave. Well, k is constant for a period of time.
So,
We don't know how the system is going to
what do you
behave.
mean? It's just a gain. It's an amplification.
Yes, but we don't know what the value of the amplification will be for
We
a
don't
period
care.
of time.
It's absorbed by gamma.
Now the issue is, how do we choose the gamma without the gamma 1 in such a way that it's able to compensate for whatever case scenarios we might get from k?
No, gamma is your parameters. Huh?
Yes, we
You are
choosing-
selecting this gamma.
Yes, exactly.
And then you are saying I'm selecting gamma
Mm,
equal, as I gave you, as this example, I'm using
Yes.
it equal to 5.
yes.
So whatever the value of k over k0,
Mm,
the value of gamma 1 will change in this equation here.
yes.
And it will give you a multiplication that is equal to 5. So you don't care about it.
So, but based on the expression of the MIT rule itself, gamma 1 is actually what is being expressed there, right? Initially,
This gamma. This gamma 1.
gamma 1.
طيب we
Yes.
don't care. Now what we want is this. Derivative of theta with respect to time is equal to this. And this gamma is your parameter of selection. You select it. So if you select it equal to 5, you can make the ripple effect. If this is equal to 20, this will be equal to 0 to 5. If this is equal to 10, this will be equal to 0.5. But in this equation, it's always equal to 5. It will be absorbed because this is a ratio. It's a real value multiplied by gamma 1. We are going to combine both of them together like this. So gamma multiplied by k over k0, this one, it's only a number. You understand what I'm saying here?
Yes, but again, like k over k naught could be greater than 1.
Could be,
It could also be less than 1.
could be. We don't care.
But then
It's constant.
that would change how gamma is going to be.
We don't care. As long as this gamma is constant. It will change this gamma.
Yes, it will.
Right. But this one will be always
Constant, yes. But then how do we make sure that if the system parameter k, for example, after a period of time changes, the gamma we choose finally is able to correct for that change?
You mean guaranteeing stability and others? This is your question?
No.
How to guarantee the specification in terms of stability, I will show you later, because right now we don't know how to do it.
Yep.
We are using some kind of approximation. But in terms of, there is a concern that this gamma may not work for stability. But once I select this gamma that works, it will work all the time, because even if this gain changes to 1 million, this one will be 1 over 1 million to give me this one equal to 1, if I fix this one equal to 1. You understand what I'm saying? So this gamma is equal to gamma 1 times k over k0. And I selected this gamma to be fast. This is my selection. This I don't know.
Yes.
So this times this will always adapt to give me 5.
I don't care about the value of k and gamma 1.
I don't care about this one. Because I absorbed in the fact that gamma.
So Professor, we are trying to get the.
It's like I'm saying you 3 multiplied by whatever is equal, and I would like you to have it equal to 5. So you tell me, okay, I'm going to select 5 as the multiplication. And there is a auto tuner that will, whatever happens, it will change to give me always multiplication of 5.
For a desired response, K dot. It seems as if you are not, how are we considering particular K dot in our control?
How we are considering
A
particular?
particular value of K dot in our control.
K naught is your selection, it's coming from your reference model. You know. You know your signal has to have an amplification of 5 or 10 or 1.
But our gamma here, how does it know the different values of Q naught are selected?
We don't care. The multiplication gamma 1 times k over k0 will be always equal to 5. So gamma 1 will change. And gamma 1 changes.
Depends on.
I don't sorry. I don't care about it. I don't care about what gamma 1. I don't really care about it. All what I care is gamma 1 times k over k0 is 5. So if I give you k over k0 equal to 10, how what will be your gamma 1? Ah, 0.5. If I tell you k over k0 now is 20,
So
you just change gamma 1. Gamma 1 will change. It's tell me, okay, it's equivalent to gamma 1 equals 0 to 5, for example. Okay? If I tell you k over k0 is 1 million, then you're going to tell me this is equivalent to k over 5 is equal to k, gamma 1 equal 1 over 1 million. As long as the multiplication is 5. What I'm going to implement is the last equation, which is minus gamma times e times ym, and I'm going to select the value of gamma. How to select the value of gamma? This is a question that we need to answer. But I can still do it. I can still select gamma. Does it make sense? This is, by the way, this trick of combining parameter or coefficient that are constant in proofs is very used in many theorems, just to reduce the complexity of the system. Especially gamma, we select gamma, it's free. Huh? All right? Make sense?
Yes.
Let's see how it works. Okay, I'm going to do this, and then we see how it works. So many people, when they see MATLAB, they believe, huh? I think this is the one that we need. See. You are able to see the, is it clear for you? Yes? Alright, so what I have is this. This is my system. And this my system has a gain equal to 1 and the time constant equal to 0.1. The example that we took assumes that the dynamic of the system is, no, only the gain k is changing. So I'm using my reference model with the same dynamic, 0.1 multiplied by s plus 1. Everybody is okay with this? But the k naught that I want is 10, not 1. Everybody is okay with this?
Yes.
Alright. Now, the error is telling me here the way to compute this value of theta. I need first of all to compute the error between y and ym, the error. So this is y coming from the system. Right? This is the value of y. We come back to theta. And this value of y goes here. We take the derivative of, not derivative, but the minus ym. So y minus ym, this is the error. Then I'm multiplying this by ym. So this is e times ym. Then I'm multiplying this by gamma. This is the gain gamma. Right? And this will give me the derivative of theta with respect to t. But the controller, u, is equal to theta times uc, not the derivative.
To integrate.
So I need to integrate. So I integrate this derivative. This will give me theta. And then multiply it by uc. This will be my controller. This is my control signal. Right?
Yes.
Then what I did, I imposed the change in the gain. So I put here a function that changes with time. right? And it will come and multiplies the output. It amplifies the output. So the system goes from 1 to any value that I put here in terms of change, and it's a decreasing value. And then I would like to see what happens with theta, because this one will not change. It's always equal to 10. I'm fixing it equal to. This is my reference. You agree with this?
Yes.
So I
Tutor, I think what
multiply by
you
10.
multiply with step.
I multiplied here with a step
Yeah.
because I want. It's not a step. It's like an amplification, but the amplification happens at one particular time, not all the time. So in order to make sure that it's time synchronized, I just put a step. This is the easiest one for me.
So
Yeah,
it starts with the
after
one,
some time.
and sometime you go to 3 or 4,
Exactly.
something like that.
So the gain will go. The gain will
From
start
one
After
20.
20.
after 20 seconds.
Go to
It
half.
will goes from 1 to half.
Oh.
A decrease. Just artificial, just to see that the system, how the system would behave with respect to time change,
New gain.
new gain. So the new gain is K. K, it's a new gain.
So gamma it will change after 20 seconds.
Gamma will not change gamma. It's always equal to 1.
Overall, not overall it's constant, but internal gamma.
Internally, gamma 1 would have to change, but I don't see it,
Yeah.
and I don't care about it. But what we'll have to change is theta. Theta is here. This is the signal theta. So this is theta. So this is theta that I'm going to observe here.
Theta is my control from the UC and from the new adjustments
Yes.
coming from the model, my desired model.
Exactly. Any question about this? Is it clear what I did here?
So I check my desired model, I get from it the error and multiply the error by gamma, integrate it and add it as a new parameter to the control.
Exactly. Every integrator has, of course, an initial value. Huh? So if you have an initial value of the controller, you can put it here. I'm putting initial value equal to 0. So I'm assuming
And my initial control will be
0.
UC will be 0.
UC is a
Coming
is a
from
staircase, I think, if I'm sine wave
what? Final, okay.
with an amplitude of 10.
It's my initial control.
This is your initial input.
Initial input.
But your initial control at time 0 will be 0 because my initial value here is 0. Theta is 0. So the system will not do anything.
So multiplication. I'll multiply it.
Exactly.
Manipulating the sine signal by the amplitude and phase using the what they call it, new phase.
I'm going to reduce the amplitude of this from 10 to 1 just to make sure that we are getting what we have to do. I don't remember what should be the value of the input. We'll see how it works. But the program is clear. صح يا Sumili? There's nothing difficult. So this is my simulation. So I'm comparing my reference also to my output in order to see how well I'm doing. My reference YM to my output. Where is it? So let me close it and then we'll try it again. Why is that not good? Maybe because I have many windows open. Anybody knows why it's not open?
Change the scope.
It's open?
I think it's
Ah, it's
Change
behind
it.
the scope. But I'm not seeing it.
Just change the scope.
What do you mean change the scope?
Delete and create.
في error جاء.
delete it and
delete it and then replace it again. Why؟
علق.
علق تحت. في مشكلة في خلاص نقول هذه. We take it out. Then I know why it's not working. Because I have another similar open. So we go open here. Then what we said, we are going to change this one to 1 or 2. I think it's opening somewhere else. I don't know where.
Okay, that is good.
Cutting rope. Is open to symbolic model. I think one should be closed.
I'm not very conversant. So.
Alhamdulillah.
Sometimes,
Sometimes you talk about technology and adaptive control and all smart things, and then at the end you find out that there is an issue. Controller does not work. Alright, see here what I did is that the system is trying to adapt, okay? So I start with different gains. 1 equal to 10, the other one equal to 1. And then the system starts correcting. You see here, there is a correction action coming. Up to this point, in this correction action, he has almost the error equal to 0. Then I change the controller. I change the gain.
yes. So
And then you see now it's different because they have different gains, and the system is trying to recover again and identify again. If I come here and I change the gain, then it will do exactly the same thing. And this is every 20 seconds. I can do it here, right? So, but you see the correction that is coming from the system. The system is trying to correct and reach what we want here in terms of values. But I can accelerate the adaptation because the value at this type of adaptation means that theta did not reach what I want, right? So theta here, you see, this is I started with theta equal to 0. The system, the reference system K0 is 10. My system is 1. So theta has to be equal to 10. So if I have here the reference signal is 10 and K is equal to 1, the difference between them is a factor of 10. So I need to have equal to 10. So theta start changing and the target is to reach 10. And the speed of convergence is this. It takes for theta 20 seconds to be able to reach the value of 10. And when it reaches the value of 10,
Change it.
I change it to something else. Alright, so it has to go to 20 now. And this is the time for convergence. Everybody's okay with this?
So here is theta of t.
This is theta of t.
Why not this linear? Because we have constant value for.
Theta of it's not linear. Theta of linear is equal to e multiplied by ym. This is derivative. So whatever e, whatever ym, the multiplication will give you the value of derivative.
But it's constant.
What is constant?
d theta over dt.
It's not constant. If it's constant d theta of dt, then
How can we change it?
changing with e and ym. So what should I do to make it faster? Change gamma. Right. So what do you suggest? 2? Double gamma?
Let's stop.
Let's not be as. So the value of gamma is here.
Already it's now 1. Okay, it took 20 seconds.
أيوة. It's minus 001. So we are going to put it equal to 1. Minus 1. Everybody's okay with this? So I changed gamma to minus 1. Right? And the way I selected it is just random. I did not look to the value of k or k naught, nothing. But we'll have to look at them later on, but this is something else. So this is my response now.
Faster.
Much
Much faster.
Right? And then if you look to the speed at which theta was able to correct itself, see, this is theta. Just by, it was 001, so I made it 100 times faster. So it gives me very quick. It converges maybe in 0.1 second. And theta here is constant. So the controller was able to reach the reference. And then I made the jump and it reaches in maybe another 0.1 second. And then the controller was able to reach again and correct. Everybody's okay with this?
Yes, sir.
You understand now the problem of time versus
What
speed
about
and the
you?
change of theta? Huh?
What about control law? U, the signal of U, it's changed big or?
We will see you. This is a good question. What was you during this process? Okay. And this is something that is very important for us. But there are two things that are very important that I would like to do with you before you leave. Let me put this one. This is the controller for the process. Huh? For the system. This is what you are doing. So the controller is reasonable. Right? It goes to 20 because the difference between them, and then after that, it oscillates.
Actually, it depends on the system here.
Yeah,
If you have DC.
remember, UC is 2, but the gain of the system, K naught, is equal to 10. So we are expected to reach 20. And this is why your control reaches 20. Huh? And then after that, we
Yeah.
reduced by half, so it has to reach 40 again. Everybody is okay with this? So, if I change the input from 2 to 10, as it was before, so now I have my input 10, my K naught 10, the gain of the system equal to 1. So I'm expected to reach a control equal to 100, because 10 times 10, in order to get what I want in terms of output. Right, so this is how it looks like. Almost
Immediately.
perfect. There is there is some kind of error here at the beginning, at the start, but after that, it's almost not there. See here? But there is some kind of behavior association here. It's okay, acceptable. Everybody is okay with this?
Yes, sir.
And I'm done. So if somebody tells me the gain after maybe another, let's say we increase it, after 20 seconds we go to 2, we are expecting the value of theta to go down.
Down.
No.
Huh? So theta was up and then it goes down. Everybody's okay?
Yes.
You see the oscillation that we have here? It was not there before. But now we are seeing oscillation because we are using high gains on the system. This is how it looks like. And then if you go to look to theta, to you, the control, your output is nice, huh? Your output is beautiful. You cannot find the, and if Trump was here, he would say this is really, really beautiful. It's a really beautiful output. But if you look to the control signal, you will see the control signal has oscillation. It does not appear here with the naked eye, but if you look carefully, this is how the control is behaving. So there's some oscillations in the control head. So this confirms that the dynamic is not linear. Something else is happening. Everybody is okay with this?
If we play with initial condition for theta, because here is 0,
Yeah.
so what happens?
It will be the same except that you are going to have, for example, theta, you will take it equal to 1.
Yeah.
You will see the control starting from 1. It's not an issue. So if you see the value of theta, you will see theta starting from 1 now, no longer starting from 0.
But the oscillation in the first time is increased.
See here starting from 1, not from 0. If you zoom on this part, you will see it's starting from 1. But it's not the oscillation, of course, it will increase for different factors. These are different factors. Now, if I go back and I say I'm going to select a very different value of gamma, let's be more greedy. Gamma equal to 10.
Change the integrator.
Okay.
Yeah, which is the same as this one.
No.
Same multiplication. This one is beautiful still. Nice signal. But if you go to the value of u, this is how it looks like. You see the oscillation, and if you go to theta, you will see similar behavior for theta.
If we make more large sigma, can this take us to an
Sigma?
gamma?
Gamma.
Can this take us to an unstable system maybe?
It will. And this is what I will show you next time, inshallah.
So we will have some constraint to our. We will make some constraint to our
Value of
gamma.
Value of gamma.
Yes.
Yes, but we'll see how to select gamma. That's the question. So what I will do next time, I will make the example a little bit more complicated. I will go to. In fact, I can show you this now. Same feed forward, but rather than using first order system, k equals 0.1 times s plus 1 and as a system, I will use a second order system. So it's very simple again. Let me move this. So it's a second order system. Exactly the same structure, but only the gain changes. Something is going on, but it's okay. I think I'm
Doctor,
losing
this
it.
is probably because the version of MATLAB. Maybe it's create this one in the previous one.
Maybe it's converting this. This is why it's stuck. But it was not stuck before in my office. Yallah, let's try it. So this is the second order system minus 0.1. I need to see what is the value of
Okay.
k.
K equal 1. K equal 10.
So I'm using the square wave now, not the sine, and I'm using an amplitude of 0.1. And I'm using the same gain 10, 1, and then gamma equal to 1. So if I put the signal, you see here the difference between, this is your reference signal, the yellow one. I need to let you go, but it's very nice to see this. This is your reference signal, but your reference model has a gain of 10. So what you put here, 0.1, has to be multiplied by 10 to give you 1 as output. So what you are getting in the output, the blue is your reference signal, the brown is your system, how your system is trying to respond. So he's trying to correct here, he was not able, we changed, he corrected better, then he got it even better, and then he was perfect. Right? Everybody is okay with this?
Yes.
So now what I'm going to do is changing, as I did before, the amplitude from 0.1, I'm going to put it equal to 2. So only the amplitude of the input. I'm not changing anything else. only the amplitude of the input. So my controller, the algorithm is perfect except that I decided to change and use a different input level. And the system is completely unstable.
Oh.
So it goes to 10 to the power 55. So all what we did is changing the input. We did not touch anything on the controller and the algorithm. Everything is beautiful and nice and splendid, but it becomes completely unstable.
So gamma is not enough now.
Gamma is not good anymore.
You need a different gamma.
So I multiplied this by 2, I will go to gamma and they will say, let me reduce gamma by, it was 0.1, I put it to 2, 20 times. So I will put gamma maybe 20 times less. 1/20. Alright?
Okay.
Everybody understood why I put 1/20?
Yes.
Because the control was 0.1, I put it equal to 2. Still not. So I need to make it even smaller. In fact, I need to put it not on 1/20, but 20 times 10. Alright? So I will put it 200. And I will show later on why we are putting this kind of thing. Okay? So we'll see how to select gamma. And what we need to know, we need to have at least a guideline, something, rule of thumb that will tell me this gamma could work. Maybe not the full answer, but at least range. What did we do today is okay?
Yes.
Clear? So this is much simpler than just looking to